In the last couple of videos, you learned how to communicate with concurrently running threads. In this video, I wanted to visit in more depth the types of memory that concurrent threads have access to. In the introduction, I told you that each thread has its own stack for local variables and method calls. One thread doesn't have access to another thread stack. You can think of the stacks as silos. Every concurrent thread additionally has access to the process memory or the heap. This is where objects and their data reside. This shared memory space allows all threads to read and modify the same objects. When one thread changes an object on the heap, these changes are visible to other threads. This has some inherent problems associated with it, which is what I wanted to discuss in this video. I've got a new project open and I'm calling it multiple threads. I'll use this project to fire up a couple of threads and look at what happens when our threads work with these different memory spaces. To start with, I'm going to create an enum called thread color, which will allow me to colorize each thread's output differently, making the output hopefully easier to read. I'll create a new class, an enum, and call it thread color, and I want that in my dev.lpa package. Before I add my enum constants, I'll first add a private field, a string, for color that will consist of ANSI Unicode characters. I've got an error on that, and if I hover over that error, IntelliJ suggests I add a constructor parameter. I'll do that. Now, I've got a constructor that takes a string, the color, and sets my enum color field to that. Notice also the semicolon that got added by IntelliJ before the declaration of my field. I'll get rid of that. I'll add my enum constant values now with the constructor declared for each that will define a string. This string, when printed, will make all the following output be that color. Each of the strings I'll be using are ANSI representations of a special combination of characters that for most operating systems will change the color of the console's text. I can reset the color as well, so I'll start my values with an ANSI_reset. I'll next set up ANSI black and ANSI white. If you're using a dark theme, you might want white text. The rest of the colors I'll list in alphabetical order, starting with ANSI blue, then ANSI cyan, which is a bright greenish blue. I'll include green and ANSI purple. Next, I'll have ANSI red, and finally ANSI yellow. This should give you enough colors, depending on your dark or light theme, to be able to see multiple threads output statements printed in different colors. One other thing I want here is an accessor method for this color field. I'm going to use the records way of creating an accessor and skip the get prefix. This needs to be public and return a string. And I'll just return color. Next, I'll create a class in addition to the main class, and I'm just going to add this in the main.java source file. I'll call this stopwatch and it'll have a method to count down to 0. Hopefully you remember, the only access modifier I can use is no modifier or package default. My stopwatch will count down by some unit of time. For this, I'll have a local variable, a time unit, called time unit. I'll use IntelliJ to generate a constructor. Next, I'll set up a countdown method. This will be public void called countdown with one parameter, a unit count, and integer. I will assume my running threads are going to be named by their color, so first I'll get the thread name and put it in a local variable. I'll initialize another local variable, thread color, to the ANSI reset enum constant. I'm doing a little defensive programming here so that if the thread name isn't a valid enum value, my code won't throw an exception. I use the thread name with the enum's value of method to get a thread color instance. If for some reason that failed, I'll catch the error and just ignore it. The thread will use the system color because it will be set to ANSI reset. Now that I've got the thread color, I'll continue. I'll get the string value of the color by calling my color accessor method on that enum and assign it to a local variable. I'll set up a for loop to do a countdown. You can imagine that this might be minutes or seconds. I'll default to starting with the unit count, the method argument, and count down by 1 for that. I'm going to use my time unit variable to have the stopwatch wait at certain intervals before it decrements the count, so I need to catch or specify an interrupted exception. Here I plan to catch it. I can pass one to the time minute sleep method, so if my stopwatch unit was minutes, this would wait a minute before decrementing the value again. I have to catch the exception, and I'll just print that out if I get it. I use a printf statement, so this all fits on one line. This will print the color string, the thread's name, the value of I, and a new line. That's my stopwatch code. I'm going to add an overridden method to this so that the default unit count will be 5. I have a second method called countdown that has no arguments. This will delegate to its overridden method, passing it 5 as the default unit count. I included this method so that when I create one of my threads, I can demonstrate how to use a method reference, which this method will allow me to do. Now, it's time to test this out. Moving up to the main method, I'll create and set one thread in motion. First, I'll create a new instance of stopwatch, which will count down in seconds. Next, I'll create a thread called green using new thread. My runnable will call the countdown method that has no arguments on stopwatch, so I can pass a method reference for this. The second parameter is thread name, and I'll use my enum and the ANSI green value's name to name my thread. Finally, I'll start my thread running concurrently. If I run this code, I'll see a message printed to the console every second for 5 iterations. Hopefully, you'll see that the text is printed in green in your IntelliJ console. This doesn't work for all operating systems and IDEs, but should work for IntelliJ and Unix operating systems as well as Windows. Okay, so that was a bit of setup. Let's fire off a few more threads. I'll set up a purple thread starting out the same way. Instead of a method reference, this time I want to use a lambda to set the unit count to 7 for this thread, meaning this thread will be a stopwatch for 7 seconds. I'll make this thread's name be ANSI purple. For the third thread, I'll copy the green thread's declaration and paste that under purple. I'll change the variable name to red and the thread color to ANSI red. Finally, I'll call start on these two new threads. Purple.start, then red.start. Okay, so let's run this. And hopefully you can see that each stopwatch thread is running, counting down from the method argument that it was called with. Purple was called with 7 seconds, so it's counting down from 7, 1 second at a time. In each of these threads, the unit count is a method argument, and therefore it's stored on each thread stack. Each thread has its own version of unit count, for example. What would happen though if I made the I a variable in my for loop, not a local variable, but a field on my stopwatch class? I'll add a private int I variable on stopwatch, and I'll change the for loop in the countdown method. Would you ever do this? Probably not, but play along with me for a minute or two. I'll run my code again. Something very strange has happened. First, it looks like they're all counting down from 7, or yours may have started with 5, and we only had one of our threads, the purple thread, set up to count down from 7. Second, the threads don't appear to be decrementing by 1 second each anymore. Looks like they're even decrementing by 2s and 3s in some cases. What happened? Well, first, we're sharing a single stopwatch instance among 3 threads. In my main method, I only have one stopwatch instance set up. This wasn't a problem when the state of the stopwatch instance was unimportant to the countdown operation. When we changed the variable I to be a field on stopwatch, we told all 3 threads to share the I field. Since our 3 threads were kicked off at the same time, they all arrived at the countdown for loop at about the same time. Each initialized or set the value of I. So why did green win? If I rerun this code a couple of times, they'll either start with 5 or 7. It's really last man in. That gets to say what I will be when these threads get around to printing I in the first iteration. Maybe purple got their last in one case, but red or green got their last in the next run. Because this loop variable is shared, by the time a second elapses and these threads go to print the value of I will have the value in it from the last thread initializing it at the start of the for loop. It might even be decremented for two threads before they have a chance to print its first value if the first thread was able to decrement before the other two had their chance to print. This exercise demonstrates that our threads are all changing the field I, and those changes are visible to all threads as they progress in their work. This has pretty ugly consequences for our stopwatch behaviour. None of them are keeping time correctly or counting down correctly. The other thing I want you to grasp is that none of these operations, not our method as a whole, or one iteration of this full loop, or even the print statement alone, is what's called an atomic unit of work. Each operational statement is split into much smaller pieces of a task. Between each of these much smaller bits of work getting accomplished is an opportunity for another thread to have its moment on the stage. This is called time slicing. Time slicing is also known as time sharing or time division. It's a technique used in multitasking operating systems to allow multiple threads or processes to share a single CPU or central processing unit for execution. Available CPU time is sliced into small time intervals which are divvied out to the threads. Each thread gets that interval to attempt to make some progress on the tasks it has to do. Whether it completes its task or not in that time slice doesn't matter to the thread management system. When the time is up, it has to yield to another thread and wait until its turn again. Unfortunately, when your threads are sharing heap memory, things can change during that wait. The Java Memory Model, or JMM, is a specification that defines some rules and behaviours for threads to help control and manage shared access to data and operations. I'm not going to cover all of this specification, but I will touch on some important points and techniques to prevent problems. First, you have to understand the problems, two of which include the atomicity of operations. I've explained how few operations are truly atomic, and this leads to problems with shared objects because of time slicing. Synchronization is the process of controlling thread access to shared resources. There are multiple ways to do this, and we'll be getting into this in an upcoming video. This feels like a good place to end this video before it gets too long. In the next video, I want to use my stopwatch example to talk more about these issues, so I'll see you in that next video.